Alright, what I want to do today is look at this particular limit, and we've come across this previously when we were evaluating limits numerically using tables, but today I'd like to look at a proof as to why this is true. So before we can get to the proof, we need a couple of other preliminary results that we're going to use during the proof, and the first one is with respect to the area of a sector. Now, a sector is a segment of the circle. I've got in blue a section of the circle labeled, and the angle shown is theta in radians. And what I'm going to try to come up with is a formula for the area of a sector. So I'm going to use the concept that the area of a sector compared with the area of a circle would be proportional to the angle at the center to the angle of the full circle at the center, which we know would be 2 pi radians. Alright, so you just need to take a second and get your head around that concept. Alright, so now I'm going to do a substitution. The area of the sector I'm going to call A. The area of the circle we know is pi r squared, and that's equal to theta in radians, as we've defined, over 2 pi. Multiply both sides by pi r squared, and a wonderful result happens, that being that the pi's cancel out, and our formula is therefore the area of a sector is 1/2 theta r squared. Alright, I will need that formula shortly in my main proof of the limit I'm trying to show. We need one more result, and that result is called the Squeeze Theorem. Alright, so the Squeeze Theorem says, and as I read it, I'm going to draw it. We have three functions f, g, and h, which are continuous on the closed interval AB. And we're told that f of x is less than g of x is less than h of x for every value of x in the interval. And if c is between a and b, so let's put our c in at that spot, and if the limit of f of x and h of x approach L, okay, so I'm going to put in my f of x in blue. At L, it's got to be approaching c. Let me put in my h of x in red. Now again, it has to be approaching L at c. The function is then saying that g of x, whose y values are between f and g, would mean that the limit as x approaches c of g, in green, must also equal L. Basically because the three functions are squeezed together at that point. And that is the Squeeze Theorem. Alright, so now we are ready for the main event. The main event being that we would like to prove the limit as h approaches 0 of sine h over h to be 1, h in radians. Alright, so what I'm going to do is I'm going to show it first of all from the right side, and the proof would go similarly from the left side. I need to show it from both sides, but I'm only going to do it from the one side, and then I'll just say that from there it would be similar if we did it the other way as well, just to give you an idea as to how this goes. Alright, so we have, first of all, we're going to take a unit circle, which means that the radius, so I'm just going to draw in quadrant 1, a unit circle of radius 1. So this coordinate is 1, 0. Let's call that point B. Let's draw an angle. Now the angle is h in radians, and where it intersects the circle, I'm going to call P. I'm going to call the origin O. And the only other thing I'm going to throw in here is I'm going to draw a vertical line through 1, 0 like so. And the intersection point right here, I'm going to call Q. Okay, let's just label what these points would be. Well, since this is a unit circle, which is radius 1, we know that this coordinate here would be the coordinates cosine of h sine h. Because we know by definition cosine is the x-coordinate on the unit circle, sine is the y-coordinate on the unit circle. So that's this point right here. We've got the point down here labeled as 1, 0. Alright, now this point here, we're 1 unit over on the x-axis, so that's 1, comma. Now this side right here, I'm looking at this triangle, we need to determine. Alright, since it's a right triangle, I could say that the tangent of the angle h is something over 1, which would mean that the missing side, labeled question mark, is tangent h. In other words, this distance here is tangent h units up, which makes the coordinates of this point 1 over and tangent h up. Alright, now you might say, why did I label the diagram like that? Here is what I'm going to do. I am going to find 3 areas. I am going to find the area of triangle OPB. Okay, and let's just do that while we're here. So the area of a triangle is 1/2 the base times the height. The base is 1 unit over, and the height, right there, what's this vertical distance right here? Well, it's going to be sine h. So that's sine h. So that reduces nice and simply to sine h over 2. Next area I'm going to calculate is the area of the sector OBP. So it's this curved section in here. And previously we came up with a formula of a sector to be 1/2 theta r squared. And our theta, which is our angle, is h, and the radius is 1. And so that reduces to h over 2. Finally, I'm going to calculate the area of triangle OBQ, like so. Okay, this is a right triangle, and so the area of that triangle would be 1/2 a base of 1 and a height of, right here, tangent h, which reduces to tangent h over 2. Now, this triangle's area will be smaller than this sector's area will be smaller than this triangle's area, because as you can see by the picture, that is the case. So what I'm going to do with that is I'm going to say that sine h over 2 must be less than or equal to h over 2 must be less than or equal to tan h over 2. And an area must be greater than 0. So I'll put greater than 0 in that spot. Alright, so what I'm going to do now is, now that I've got this expression set up, I'm going to manipulate it a bit. So I'm going to multiply everything by 2 over, so I'm going to let me write this down, I'm going to multiply by 2 over sine h. Now, since the angle that I'm working with is in quadrant 1, the sine of h is positive, so 2 over the sine of h is positive, because we're in quadrant 1. Now I'm thinking about that because when I multiply an inequality, the signs may switch direction. They won't in this situation because I'm multiplying by a positive. Alright, so here I go. I'm taking this quantity here, and I'm multiplying it by each of these sections. So 0 times this is 0. If I multiply this by this, I'm going to get 1. If I multiply these two together, the 2's are going to cancel out, and I'm going to get h over sine h. And if I multiply these two sections together, I'm going to get tan h over sine h. Alright. Now, I am going to just focus on this section, okay? And what I'm going to do is, you can see I got my sine h, or I've got h over sine h, which is looking close to what I'm trying to show, which is sine h over h, except I need a limit involved. So what I'm going to do is I'm going to take the reciprocal of each of these quantities. And when you take the reciprocal of two things that are positive, for example, 1 is less than 3. If I were to reciprocate both sides, you'll notice that the opposite side is now larger. And that's a property of inequalities. So I'm going to reciprocate everything here. The reciprocal of 1 is 1. When I reciprocate, I said the sign is going to switch. That's going to switch to sine h over h. And this is going to reciprocate to sine h over tan h. Okay. And I'm now going to write it just in reverse order. Okay, I've done a couple things here. I've just written it instead of in this order, the reverse order, so the signs have switched. And I'm breaking this up into sine h over 1 times 1 over tan. 1 over tan would be cos h over h. That allows the signs to cancel. I then have cosine h is less than or equal to sine h over h is less than or equal to 1. Now you're sitting there wondering, I'm sure, okay, but this is great, but where's the limit? So we're going to take the limit as h approaches 0, and we said we were working from the positive side of all of these quantities. And I'm going to evaluate these. As h approaches 0, cosine of h goes to 1. This quantity, I'm not sure, so let's leave it like that. And this quantity, the limit of a constant, is that constant. So we have this limit that we don't know, but we know that it's between 1 and 1. So by the squeeze theorem, therefore the limit as h approaches 0 from the positive side of sine h over h is 1. Similarly, you could prove that coming from the negative side is 1. Therefore, completing the proof, the limit as h approaches 0 in general of sine h over h is 1. Alright, now there's just one other trig limit we're going to need to be able to work with. Alright, so what we're going to do here is we're going to multiply numerator and denominator by the conjugate of the numerator. If I multiply out on top, I'm going to get 1 minus cosine squared h, all divided by h times 1 plus cosine h. From our identities, you have an identity sheet, 1 minus cosine squared is sine squared. So I can make that replacement. And then I'm going to break up my last step as follows. Sine h over h times, well, we've already shown that this is 1. And let's try to evaluate the second part. As h goes to 0, cosine of 0 is 1. 1 plus 1 is 2. So we have 2 over sine of 0 is 0. So we have 1 times 0 is 0. And therefore we've proven that the limit as h approaches 0 of 1 minus cosine h over h is 0.